IT, following a master's degree in computer science from the University at Albany, and a BS in electrical engineering from Tsinghua University in Beijing. Currently, Dr. Luo is an associate professor at Northwestern, the founding director of the Center for Collaborative AI in Healthcare, and the chief AI officer at the Northwestern University Clinical and Translational Sciences Institute. We're thrilled for Dr. Luo to be here. And I'll turn it over to Yuan. Thank you. Also, just a reminder to folks, if you are not speaking, please keep yourself on mute. We'll have time for questions as we go along. Thanks.
Thank you, Tom, for the introduction. And it's a great pleasure for me to be here talking about some of our recent works in developing and applying large language models for clinical and translational science. So as a beginner, just want to show this recap on some of the large language models. In the field of NLP, and perhaps the most significant development recently is those large language models. And two representative architectures are BERT and GPT. But while GPT only considers the left context when making predictions, the BERT model takes into account both the left and right context. So it's a bidirectional model. That's where it comes for its name. And in addition to the architectural differences, the earlier model, Elmo, is a feature-based approach, but BERT and GPT are fine-tuning approaches, and these will be our focus. So this talk will cover our recent work and reflections on multiple categories of healthcare tasks, ranging in all over clinical and translational science. And they include medical and scientific communication and medical resource building, and also assisting clinical practice, and last but not least, informing public health surveillance. First, let's take a look at using ChatGPT in terms of helping with the medical and scientific writing, or if you may put it, not helping. So in this study, we evaluated the abstracts that are generated by ChatGPT for 50 scientific medical papers, and we gathered the titles and original abstracts from the current and recent issues that are published in late November and December of 2022 from 5 high-impact journals that include JAMA, New England Journal of Medicine, and BMJ, Lancet, and Nature Medicine, and compared them with the original abstract. And the question that we wanted to ask is whether humans can reliably differentiate those, whether they are generated by the medical, by the physicians and scientists, or by GPT. Right? And the prompt that we used in this model that we viewed is to please write a scientific abstract for the article with certain titles in the style of a journal, and certain link. And note that the link is superfluous here because back then ChatGPT cannot browse the internet, and its knowledge cutoff date was September of 2021. So that was the time that we used the system that we used to perform our studies. And so given that ChatGPT is sensitive to previous queries in the same chat, we ran each of the prompt in a new session independently. While all the output appeared superficially to be formatted as a scientific abstract, we found that only 8% and 16% of them correctly used the headings particular to the specific journals in the prompt. One thing that we noticed is that by comparing the reported patient cohort sizes between the original and the generated abstract, we see that the patient cohorts were a similar order of magnitude between these original ones that are generated by the humans and the artificial ones that are generated by ChatGPT. And there is a Pearson correlation of 0.76 when you try to align the cohort size, of course, when putting them on a logarithmic transformation. The GPT output detector that we used actually found a high probability of the AI generated output in many of those GPT generated abstracts. And this is compared with a low probability of those GPT generated output in nearly all these original abstracts. And so this is shown in the figure on the left. And then we find that 17 abstracts, and which account for 34% of it, they received a score below 50% from the AI output detector. And these include 5 of them with scores below even 1%. On the other hand, there was only one, which accounted for only 2% of the original abstract that scored above 50%, being considered as generated by AI. And so those represent false positives and false negatives. And so the AI output detector has then AUC of about 0.94, as shown on the right figure here. And this indicates excellent discrimination between the original and the generated abstracts. And the next thing that we looked at is these generated abstracts. They appear to be authentic in the sense that they did not appear to be plagiarized from other written work. And so we evaluated this abstract using a web crawling plagiarism detection tool, I think is Authenticate. And nearly all these generated texts were deemed completely original by this checker. And then we ask humans to review and using different criteria. Of course, those are different than the criteria that are used by the AI output detector. And then we ask humans to flag those abstracts that's being generated by medical professionals, scientists, or whether it's generated by GPT. And we actually found that it's much harder compared to the AI detector for humans to distinguish reliably those two categories. And reviewers indicate that it was surprisingly difficult to differentiate between the two. The abstract that they thought were generated by ChatGPT were superficial and vague and focused on details of original abstracts, such as inclusion of the clinical trial registration numbers and this alternative spellings of the words. And there are also other observations that noted while interacting with the model, with its use of the generated numbers and including those clinical trial number. And so ChatGPT, while it writes believable scientific abstract, but it doesn't completely generate the actual data in a reliable way. There are some of the original abstract, even without being detected as plagiarism, but they often they were identified using an AI output detector. And so this is something that is easy for AI to do, but although sometimes skeptical to human reviewers, not always they will be detected by human reviewers. And I think this is part of the reason that sometimes humans find it hard to distinguish between the two. And we also evaluated abstracts for the journals and medical conferences. That's not included in the paper, but what we found is that this work suggests that some of the policies and practices to maintain rigorous scientific standards need to take the observations that we generate into account, because then you would ask important questions like, what if that humans cannot detect themselves, but the difference can be detected by AI? And so are we completely going to rely on AI to tell us what is originally generated by human, by scientists, versus what is generated by the AI or GPT models, right? So if humans cannot detect it, then what does it mean by asking what benefits it offers to us by having an AI to tell us? And so are we going to get into an arms race of one AI that is trying to fool the readers of whether it's been originally generated by a scientist versus generated by another AI, and then we'll have another AI that always tries to outwin the detector, right? So eventually, will that put humans out of the loop for this arms race, right? So I think those are all the questions that this study prompted us to think, and especially to exert care when we craft the policies and the regulations for the in those editorial process. Okay, so now let's switch a gear a little bit. We want to talk about the resource building. And one particular applications that we are developing is to develop a resource that can facilitate interoperability, better interoperability across the integrations of the data to support multi-center studies in order to achieve diversity and also larger size cohort. So for this purpose, we're looking at a particular issue of generating FHIR resources from the clinical notes. So let me give you a little bit of background. I think some of the people here might have already been familiar with the topic of interoperability. And this is especially important when we're doing multi-center studies and in a coordinated manner. And we all know the benefits about interoperability, but in order to go there, in order to really harmonize the data and clinical notes across different institutions, we need to bridge over the barriers that are resulted from different templates of the hospitals, and sometimes even the notes types can be designated differently across different centers. You might call it pathology reports, we might call it something else, or even with the more fine-grained designation in terms of this category. And so this kind of differences can lead to many studies being not generalizable. And so in order to have this interoperable data set and to power the generalizable model building and insights identification, we will need to convert the data either to a common data model or to convert them to something that we speak as common language. It's akin to if you have people that speaks Spanish or English or French, and then I think nowadays the universally accepted language for business and academic communications in English. So just getting people to all speak English, right? So that we can talk about, we can get on the same basis, right? So for this purpose, a lot of people have focused on FHIR, which stands for Fast Healthcare Interoperability Resource. And intuitively and on a high level, you can think of it as we can convert all the different expressions in the clinical notes into a FHIR resource that abide by certain standards, and it's akin to convert Spanish to English and then convert French to English, so that we can all communicate via the same language. And there are, of course, different standards and formats and elements and API associated with this conversion. And for this talk's purpose, we'll mainly focus on the conversion from the clinical notes to the FHIR resources. One example that I get here for FHIR resources is this. So as you can see, the resource type is observation, and it's about a real-world patient's hemoglobin levels. And in the fields in this JSON file, there's different observations like the log code that are associated with the blood test and the patient's identities and the date and the quantities of the test results and the interpretations and reference ranges. And you can see that this FHIR resource format is sort of the English that allows people to communicate via the same language. And when we talk about FHIR conversion, of course, we can convert from the structured data to FHIR and then convert the textual data, clinical notes to FHIR. And then we can also even convert from FHIR to another type of FHIR resources, depending on the application usage. But in this case, as we're shown here in red, we're going to focus on from text to FHIR and from clinical notes to FHIR. So here's a more concrete example of a sentence that is taken from the discharge summaries. And so this sentence talks about medication and its dosage and its form and its route and its frequency and its indications, right? So this is illustrated in the converted file resource format on the right. So you can see all those information captured in the file resource that's converted to represent this medication statement. And then let's think about the process that's required to make this conversion or to generate the file resource. If you are doing NLP research, probably a few years ago, you would start with name and entity recognition and then get all those medications and form and route and the indications, and then classify the relations, extract the relations between those medical concepts, such as the form is of the medication, the route is also the medications, and they're related, right? So label all those relations. And then do standardization to convert everything, different measures, to the same medical concept. And if you're familiar with the Unified Medical Language System, it's a concept unique identifier that allows you to aggregate different types of expressions into the same concept, so we're speaking the same language. And then look up the concept and do the calculation, because sometimes you need to convert them into the same unit, or if they are talking about frequencies per day or per hours, you need to convert them to the same scheme, right? And then it's proper formatting so that they can be converted into this JSON type format for this file resource. And so as you quickly started to appreciate this process, multi-step process is labor intensive, and each of the steps can be prone to errors, and compounded errors can actually make the system really clunky to use and hard to fine tune, right? So this is a human labor intensive effort, and often, if you're building machine learning models, the more require massive training data, potentially for each step. And like I said, the compound or aggregation of the errors can lead to very inaccurate systems. And of course, this have high maintenance cost. Then we think from a different angle. And if you think about the input and the output is just a sentence, it's a text, and then the output, although it's formatted, JSON formatted, but essentially it can also be regarded as a text, right? So you're giving a text or a prompt, and then you are expecting some text out as an output. And then why don't we just use ChatGPT or other large language models for this purpose, and then see whether it can automate this task, and hopefully that make it more flexible and generalizable. And so this is what we set out to do. And in order to provide a accurate and faithful evaluation, we of course need to come up with the data source. So this is why we were taking the N2C2 challenge data source that has all these medications that are annotated there, but they don't have all these other informations like the dosage, route, and the indications, etc., for those identified humanly annotated medications. So this is why we took the labor-intensive effort to do this annotation on top of this N2C2 data set. So we have the dosage, schedule, reason, or indication, and form, route, and strands annotated comprehensively for all the medications that are recorded and annotated in the N2C2 data set. And so with that data set ready, then we look to evaluate to see whether we can leverage large language models to bypass the traditional 6-step approach of generating file resource from clinical nodes, to see if we could sort of giving it an end-to-end solution. And so regarding the LLMs, I think people are familiar with that. How you craft the prompts is really important. And this is how we craft the templates for the prompts. And so you can see that we give it instructions, generate instructions, asking it to capture, for example, the route. And one thing that we should note here is that because the initial token limit of those large language models, and this is especially true when we started doing the study, but nowadays I think GPT has the capability of taking 128,000 tokens. So I think that has been relaxed somehow. So if you're doing it now, you might be able to just fit everything into one prompt, but we resorted to using 5 prompts to generate the complete medication statement. And those prompts are designed to focus on medication's form and strengths and reason and route and timing and dosage, respectively. And so this example that I'm giving you here is for is for one of the categories. And then after the instructions, we took the template of the FHIR resource, which you can see is basically a JSON format. And then we give it a few examples. In this case, we give it a oxycodone, and we give it a JSON format example. And we also, of course, give it more than just one example, because sometimes that helps in terms for the system to better understand the context. And then we also give it a terminology sources. I think this is one of the places that's actually chewing up the token limit. So, and as you might imagine, that the more of the bigger the terminology sources, the more token length we will require the LLMs to be able to handle. And also note that we didn't just try with GPT-4, but we also tried with the other Llama models and also the Falcon models. And so this divide and conquer prompting mechanism is what we found as sort of a common denominator that works for all of the language models with their respective length limit of the tokens. So here's the recap of the data that we annotated on top of the N2C2. And so here we give it different categories of the annotations, the dosage, the reasons, and the strengths, and a few examples of those annotations and descriptions of what the annotation means. So for example, the subject is who is taking the medications, and the medication code is either NDC or RX norm or SNOMED CT medication. And those forms, we give it either powder or tablets or capsule or some other form. And so you can see that we have annotated a few thousands of those medications from the N2C2 corpus. And so this is our basis for evaluating, provide us with at least a sizable data set for obtaining robust statistics to distinguish the performance of different systems, and especially compare them with the existing state-of-the-art from the industry and also from the academia. So here's the comparison. So with that annotated data set, we set out to compare a few models. Some of the large language models that I already mentioned, GPT-4 and Falcon, which we used the 180 billion parameter version. And then for Llama 2, we used the 70 billion version. And then for the existing NLP pipelines, we took one state-of-the-art from NLP2 FHIR, which we developed collaborating with Mayo Clinic a couple of years ago. And also from the industry, we took a state-of-the-art system that is from Google's Healthcare Natural Language API. And here we show the code for the evaluation results for recognizing different types of the FHIR resources elements. that are pertaining to the medication statement. So across the board, we highlighted in bold the best performers across all the systems. And then we underscored the second best performers. So you can see that the best performers unanimously fell onto the GPT-4 model, and then the second best sometimes is switched back and forth between Falcon and NLP2 Fire and Google's and natural language API. So this is kind of interesting because if you think about GPT-4, it has 1.7 trillion parameters. Its orders of magnitude larger than Falcon, which is also an order of magnitude larger than Llama 2. So it does seem that the parameter sizes matters. On the other hand, the best performance actually is achieved by GPT-4 rather than a bespoke system that resulted from many hours of human labors. So this is something that is interesting, saying that not only the system can be flexible and sort of a resource, well, depending on what you define how you define resource. Well, so here we were thinking that to just adapting such a system from GPT-4 doesn't take as much effort into developing the NLP2 or Google's healthcare NL API from scratch. So from that point, we were thinking that this is sort of a resource-wise less intensive approach, or human resource-wise less intensive approach for getting those models. And you can see that this sometimes can even lead to better overall accuracy. So I think this really gives people hope into adapting some of those large language models into the previously very special and domain-specific tasks. And one of the importance that I want to emphasize here is that this resource that we have generated in the system that are used to generate the file resource can be adapted to other institutions. For example, we have been trying that locally on our local clinical nodes with some of those open source large language models, and then see that they also give pretty promising results. So without too much of a prompt engineering and also without even fine tuning some of those models. So I think this is really promising in terms of having a general purpose system that can be sort of prompted, and of course you can also leverage knowledge graph to either ground it or to refine the output, but that's another story. So here the important message is the flexibility doesn't always comes at the cost of the accuracy. Sometimes you can expect to have the generalizability, flexibility, and the accuracy at the same time. So this is really promising. And so now let's switch gear to talk about, after we have looked into the resource generating field, and what if we wanted to use some of the large language models directly for some of the very specific tasks, let's say adjudicate a heart failure observation or onset. So it's a very specific task, and then can we use large language models to help with that? And so for this purpose, we were using actually some of the earlier language models because those are open sourced and then can be easily deployed given our constraint on security and also patient identity protection. For this purpose, we're looking at transformer-based models like BERT, but we were not just looking at this BERT with the very short limit of the token length. We wanted to see that, especially in clinical context, we have long text. Clinical discharge summaries can be several thousands of characters, and if you're looking at progress reports or pathology reports and other specialty reports, sometimes they can be even longer, thousands, tens of thousands, or even more words, hundreds of thousands of words, right? So that has exerted greater demand in terms of length of the tokens that those language models can handle. And the traditional BERT and its inflected clinical BERT and BioBERT models, they are always subject to the 512 token length limit. So this is why we were seeing that whether we could leverage some of the sparse attention mechanisms and build models that have longer text token limit. Right? So this is why we're building models like clinical long former and clinical BERT that are able to handle thousands of the tokens at least. And so for this work, we were conducting a comprehensive set of evaluation of those models on 10 downstream tasks as shown in the figure here. So these ranged from name entity recognition to language inference to question answering and then to text classification. We conduct comprehensive evaluations against those tasks, all of the models that we mentioned, those with long sequence models, those with short sequence models. And our long text models, as you can see, significantly outperform all of the short text models. But before elaborating on our results, I want to mention a clinical study using the LLMs to adjudicate heart failure hospitalization from discharge summaries. And this study is not done by us. It's actually done by some colleagues at Mass Gen after we have published the paper of clinical long former. And they took our system and then evaluated against as you can see, some of these general domain long formers and the different variations of the BERT models. And then they were actually showing that our models significantly outperformed all the state-of-the-art baseline. So we really view this as a perfect underwriting of our contribution, and it's absolutely rewarding to see that the colleagues from another town acknowledge our work with their very specifically designed clinical tasks. And now let's delve into our own results. They show that the two long text models, clinical long former and clinical big BERT, they consistently outperform the short text models such as BERT, BioBERT, and clinical BERT. And this is true across almost all 4 types of the clinical NLP tasks. And interestingly, we observed that even in tasks with shorter sequences, such as medical natural language inference and OpenAI tasks, the long sequences model, they achieved better results still. And so we think this is likely because those improvements are coming from pre-training stages of the clinical long former and clinical big BERT. They were able to take more context and longer term dependencies by extending the sequence length limit. And this allows them to learn a richer contextualization of all those clinical concepts and perform better in various clinical NLP tasks. And the clinical long former and clinical big BERT that we built, they are now available on Hugging Face. And since the release, we have also received overwhelming interest and have had thousands of users access and download our models. Here's just a toy example where the clinical long former accurately predicts the next word is antibiotics, given the context of the treating pneumonia patients. And we welcome you to also test and collaborate with us to further advance this field. And especially now we have other options of the large language models, and then see if we could further extend on the context and even leveraging knowledge graph to further improve the results. So last but not least, I wanted to give some reflections on the potential use of ChatGPT, in particular in public health surveillance, such as pharmacovigilance. So pharmacovigilance primary objective is to ensure the safe and efficient utilizations of the medications. And this involves collection and analysis of the safety information, such as adverse drug events. And because 10,000 participants is typically needed to detect a real adverse drug reaction during a clinical trial, post-marketing monitoring is really important and necessary to recognize the full spectrum of drug safety concerns. But on the other hand, patients might not report all these ADEs to their clinicians. And in fact, only 1 to 10% of the adverse drug event is reported to FDA's official system. In contrary, we also find that conversations of adverse drug event, they happen more frequently on social media, which ChatGPT leverages during its training. So this gives us the idea that perhaps it's already integrated in the training data, those signals in the pharmacovigilance, and that will give the ChatGPT some of the capabilities or inclinations to be able to be adapted for those tasks. And we know that GPT-3, which is a precursor to ChatGPT, has previously been shown by other studies to identify drug synonyms from social media. And even if there is informal lexicon and spelling errors, and now we wanted to see that given that ChatGPT is the advanced version and then built on data set that captures some of the social media like Twitter, whether we can reliably detect some of the adverse drug event. And to first evaluate this, we wanted to supply ChatGPT with examples of drug-related tweets that is annotated by humans, by us. And in all 6 cases, we see ChatGPT was able to differentiate this true drug abuse cases from the false ones. And this gives us better hope. And then the next thing that we did is to look at some of those pharmacovigilance tasks. We then tested ChatGPT's ability to provide the adverse effect information on specific drug pick rate. This is approved in 2019, which is actually before the ChatGPT's training cutoff when we are using that system. And this is approved for treating metastatic breast cancer. And FDA highlighted the urgency to quickly report safety issues post-market. And overall, we found that the list of the adverse effects from ChatGPT after prompting was, in general, comprehensive and relatively accurate. So as you can see here, the first 3 bullets from ChatGPT, the high blood sugar, gastrointestinal issues, skin rash, they corresponded to the top 3 high severity ADRs that is observed in the key phase 3 clinical trial that led to the drug's approval. And the other 2 bullets, lung problems and infections, they are also confirmed from FDA and its European counterpart EMA's reports. And interestingly, there's the 5th one, liver dysfunction. This was not found in the reports, clinical trial reports when we examined, but some related lab measures were investigated, and it's hard to determine if ChatGPT actually fabricated this adverse drug event due to its generative nature, or indeed detected some signals from its training sources. So I guess this is something that could be used as an potential target that people can focus on during those post-marketing monitoring of this drug. And then we wanted to determine the cause of those adverse drug event. And I think this, as we found out, this is where ChatGPT fell short. As you can see in this slide, ChatGPT only provided 1 drug-specific cause, while the other 3, like individual variability, and so if you're looking at the left part of the slide here, so the other 3, like individual variability, were highly generic. And asking for scientific evidence to support the only drug-specific cause inhibition of the PI3K pathway, ChatGPT gives mixed results. And especially in the papers that it returned, one of them did not contain the word insulin at all, despite ChatGPT claimed so. And for the other paper, we found that the biological mechanism of how the drug can cause the hypoglycemia, they were discussed, and ChatGPT provided only a close summary. So it says that the drug inhibits PI3K, which is correct, but it does not impair insulin signaling as was suggested by the ChatGPT. So I think that part it is trying to fabricate. Nonetheless, I think ChatGPT's reply provided, I think, a valid starting point for downstream research. For example, if you wanted to use retrieval-based augmentation, or if you wanted to use some drug mechanism knowledge graph in order to run the large language models to better refine those answers, I think that it will be a very promising field for you to do if you want to further improve this accuracy. Well, so we find that with this extensive training data, ChatGPT has the potential to be a pharmacovigilance knowledge source, but it will likely not be a comprehensive one, nor can it truly reason about the potential causes, at least by without external augmentations. So another thing that we find that one of the limitations here is in terms of the language barriers, and you can probably guess that ChatGPT is trained largely on English corpus, and when it comes to the other languages like the Chinese language that we tested here, so sometimes it can confuse it with another drug, and this is true even when the chemical name of the drug is presented, is used. ChatGPT sometimes still confuses it with an antibiotic. And for those cases, I think a human search on Google could easily identify this type of errors. But for ChatGPT, for good or for better or worse, it couldn't identify those issues. So I think there is still a large gap in terms of cross-language functioning of this type of language models. So this is something that definitely requires major attention if we really wanted to make this kind of large language models functioning across the different languages that people speak. So one of the things that we think that despite all its limitations, a potentially good use case for pharmacovigilance is to leverage the ChatGPT's summarization capability for case reviews. So traditional pharmacovigilance, as you can imagine, is usually conducted by case review, and it's laborious, costly, and time-consuming, and it's because the clinical notes is usually unstructured, even if you have sections, but within each section, a lot of the times it's unstructured with jargons and also typos and acronyms all over the places. And for this, ChatGPT could help automate this process. And in particular, we supply ChatGPT with the de-identified case forms from the N2C2 database corpus for adverse drug events. And within seconds, we see that ChatGPT summarized the key medications and the potential ADEs as mentioned by the text, that those summarizations it can do with a pretty good accuracy. And so I think this demonstrated that if you use this summarization capabilities to help you record the key points and especially those targets that you are looking after, it could be potentially put to better use. So now with the mentioning of the 4 categories of the applications that we went over through scientific communications, through the pharmacovigilance, through the clinical task, clinical practice, and through resource building, we wanted to take a step back and then think about the future directions. And one thing that we find it near and dear to our heart is to make those large language models, integrate them into a streamlined and scalable NLP platform. So this is prompted by the observation that physicians often lack the bandwidth and expertise to do NLP on themselves. So what we have been doing at the health system level locally here is a bulk NLP. That is to standardize and bulk processing all the clinical notes so that we can map them from unstructured text into the structured medical concepts and relations and deposit them into common data models so that the researchers and clinicians can query, and instead of launching their own NLP pipelines. And for this, we have long been using in-house developed pipelines, sometimes also adapting the conventional pipelines like MetaMap or CTSC. But now with the advancement of those large language models, this task could also be accelerated and generalized, right? So let's say if you wanted to generalize this bulk NLP to other sites, right now you can potentially use these large language models for helping us recognize those concepts and for helping us to recognize those relations. And so I think this is at least something good to imagine, to vision, and then let's take at least the partial reality check on how good they are. So here's some of the attempts that I've tried with my Pullman's version of example. Look at the sentence: progress notes and pathology reports contain rich information on breast cancer, local, distant, recurrence, and contralateral events. And what if you ask it to do part of speech tagging, one of the traditional NLP tasks? And what if you ask it to recognize the named entities? So you can see that it's pretty good. And so for those classical and well-defined NLP tasks, I think it can do a reasonable job, even when you have certain domain specificity in the sentences. But then something happened if you wanted to do a higher level task, like parsing the sentence. And parsing is really important because after you recognize the named entities, if you wanted to extract those relations, you want to understand their interconnections, right? So you often need to resort to dependency parsing. And so in this case, we ask it to perform constituency parsing. And I think if you do NLP, you will recognize it's basically a mess, although it does look like a tree structure, but if you look into the detailed parsing, if it can be called a parsing, then it looks like a mess, right? So I think this clearly suggests the limits of if we wanted to use those large language models directly to facilitate, let's say, the bulk NLP that we have been doing for years. I think there is still a major gap that here we wanted to cross or to bridge. Another promising direction that I think that deserves our attention is sort of to use large language models to integrate the multimodal data. And in this case, we all know that large language models can learn a pretty good representation of the sentences, the text. And there are also studies suggesting that if you apply those LLMs on genetic data, like the gene former that's published in Nature last year, and some of these studies that are published on looking at applying LLMs on protein sequences, you can also convert that, learn a good representation of the genetic sequence and protein sequences. And similarly, you can convert structured data to language representation. So suddenly you can have a sort of a common vehicle for encoding the features from the different data sources. And if you think about it, it's really intuitive. And as humans, we gather information from the image, from the figures, from the tables, and look at all those scientific molecular data, and then reason within ourselves using language, right? So we do inference internally in our brain with language, and now we have something that can enable the analogous process to happen in computer, right? So I think this is something that is really interesting multimodal machine learning, in that suddenly now we have a common vehicle that could sustain the inference. And so this is something that I think is also worth exploring in the next couple of decades. And such exploration is not going to be smooth, at least. I expect that we're going to take iterative steps in order to optimize our integration of the different data modalities into the large language models. And also, as I mentioned, even in the bulk NLP case, there are some tasks that are easy to do now with LLMs, but there is also tasks that still seems to represent a major gap, right? So I think from the large language models point of view, what if we can leverage a proactive framework? For example, we know that some of those large language models are built with reinforcement learning. And what if we augment that not only to just use learning the good language representation as a objective for the reinforcement learning objective, but also to build our domain-specific objective functions into that process. And that will allow us to not only improve on the system, but also in terms of guiding us into collecting better data. Because if you think about it, the reason that those large language models are so successful is because they started from their training from very large corpus and representative and high quality corpus, right? But still, there are gaps that are hidden there a lot of the times, waiting for us to find out, and then to collect additional data to augment our existing data to address. But what if we can automate this process and let the machine learning framework tell us where the language model is still lacking and where we can collect additional data or to augment our existing data to help with addressing that. So I think this kind of migration from previously reactive to this proactive machine learning and AI framework will also be quite important into guiding those language models to do things that at realistically accurate and also reliable way. So with that, I want to close the talk and with a message that an invitation for the audience to work together and then bring this field to a whole new level. And thank you for your rapt attention, and I'm open to questions.
Wow, thank you very much, Dr. Luo. You covered a great deal in a short amount of time. I really appreciated your talk today. Let's get started with questions. It looks like there's one in the chat. It says, will we be able to access the recording of this lecture? Yes, we will. So we'll be able to make that available. Looking to see if there's anyone else who has a question, either by entering into the chat, or please feel free to unmute yourself and speak up. As we wait for folks to assemble, let me ask a question for you, in the pharmacovigilance tasks that you described, were you using the I2B2 publicly available data, or were you using another data set for this?
We're using the actually N2C2 publicly available data. N2C2 is the I think it's the next gen of I2B2's the challenge.
Yeah. And just for folks who may not understand all of those acronyms, I2B2, as you may know, is informatics for integrating biology in the bedside, which has historically been used for querying structured data, things like quantitative lab results, diagnosis codes, and so on. Really to support activities preparatory to research, determining how many patients are there with X, Y, and Z. And it sponsored an NLP challenge a number of years ago that really dealt with, physician notes. And that has then led to the N2C2. And I think this is a really good point to bring up here. The tools that we see from commercial technology providers like OpenAI, making ChatGPT available. It's important to know that any data that we enter into these methods, these commercial methods, the commercial creators get to retain control of the data. And that's why it's really important that we do not provide any sensitive Weill Cornell data to these commercial activities, because that would constitute a breach of patient privacy, which is incredibly challenging in these times, as we need to maintain public trust in science. So that's why the use of a public data set like N2C2 was so valuable here. That said, at Weill Cornell, we are in the process of standing up the use of some of these commercial technologies from Amazon, Google, and Microsoft, which includes those features from OpenAI, the makers of ChatGPT. But this was a really great illustration of the power of some of these. It looks like we have a question in the chat. Given the rapid evolution of the LLM field and rapid obsolescence of many methods, how do you design your research projects and set your research strategy? As a junior faculty, I find it's impossible to keep up. Great question.
Yeah, that's a great question. And so one of the things that I think we need to do at the medical school level is to facilitate the dissemination of all those latest developments in a rather efficient way to people, so that they can get takeaway messages really quickly and think about how they could impact their or influence their own work. And then at the side of the individual investigators, I think you could, instead of sort of thinking as an overwhelming sea that is flowing against you, you could try to think of it as a sea that will offer the flotation so that you can start surfing the field. I know it's easier said than done, but just imagine that if you can have a quick grasp of the capability of some of the models that you were not able to have like a couple years ago. Let's say if you wanted to build a registration model, build a model based on the registration data where the registration doesn't even exist, let's say for breast cancer, distant recurrence or local recurrence. So instead of spending 3 years as we did before the advent of large language models, now you could instruct and prompt your large language models to sift through all your EHR clinical notes and then to identify those recurrent cases, whether it's local recurrence or distant recurrence. And with reasonable accuracy and sensitivity, will give you a cohort of, let's say, local recurrent, distant recurrent breast cancer patients, then that will quickly give you a cohort that you can start working on, right? So on the one hand, yes, it's true. I think the technology disruption has overwhelmed some of the traditional directions fields, but on the other hand, it also enabled other fields and other directions. It's like the old saying that when God closes the door, it will open another window for you, right? So I think identifying those windows is very important to navigate the era post the launch of the ChatGPT. And at the medical school side, so what Northwestern has been doing is that we have launched a healthcare AI forum that's a bi-weekly event, and in that event will aim to give really rapid recapture of some of the latest developments. And let's say you have 4 short talks in each of 15 minutes, and including Q&A, that gives you a intuitive understanding of some of the latest developments. Let's say whether you are using large language models to represent the genetic sequence or the protein sequence in order for drug delivery, so that we let you know that what happened and then what's the input and output and how that may affect your own research. And so through this kind of educational seminars and forums, we're hoping to bring together the people and give them the sort of starting point to think about how to integrate some of those developments into their own research. So I think both directions need to converge at some point in order to really make it a scalable effort. And so we are exploring, and although I think we're moving along really good directions, but also I'm interested in exchanging ideas with folks here on what you have been attempting at sort of disseminating this kind of knowledge, and also injecting those latest developments into helping with your own work.
We appear to be over time, but thank you all for joining. Many thanks to Dr. Luo for sharing so much of the work that he and his team have carried out at the Northwestern CTSA Hub. Again, we really appreciate you joining us, and we look forward to checking in with you again soon. Take care. Thank you, everyone. Much more to come. Bye.
Thank you for having me. Take care.